Question 3. Part A. Part A, you see some questions about linear programming and subprogramming. State 2 different circumstances under which a linear program has no optimal solution. So what can happen for a linear programming problem to not have an optimal solution? Yes?
But it's unbounded.
Pardon?
But it's unbounded.
When it's unbounded, right, the rest is a sort of a mumble. I think you're confusing it with having several optimal solutions. But if it has several optimal solutions, that doesn't mean that it doesn't have any. I'm asking about when it has none at all. And the second circumstance? Anyone? Yes, if the g function can't reach 0. That is a symptom, but the circumstance is really called that it's infeasible. This is a full answer to part 1. Good enough. If you write the g function can't reach 0, that is not as good, but it's also correct. It's a bit too specific because it already assumes that you're trying to find a feasible solution using the first stage procedure, which you don't necessarily always have to do. The only way we've learned so far, but we're going to learn another way in the second year if you've chosen to. But yeah, I would also take it as correct. Okay? So infeasible means there are no feasible solutions at all. Unbounded means that's the second part of the question. What does it mean for an LP to be unbounded? It means that it has feasible solutions with arbitrarily large projected value. This is maximizing and more than minimizing. So the picture that goes with it, I'm sure you remember, you have a linear program where the feasible region might look like this. And you're maximizing, for example, in this direction, there is no bound on how large you can make the objective, so there is no optimal solution. So any solution you can find, you can always find a better one. Nice. All right? And the third part of this question asks you how the simplex method realizes that there is that the LP that it's trying to solve is unbounded. Anybody remember? No? Okay, we realize that the case is when you're doing your pivot step. The first step in every pivoting, first sub-step in every pivot step is to find the pivot column by looking at the objective row. And you find something in the objective row. So, for example, I'll take. What am I going to take? I don't have a suitable tablet. Well, you find something in the objective row which has the wrong sign. Wrong sign means negative if you're maximizing and means positive. And then you're looking for the pivot element in that column. Now, in that column, you want to pick a pivot element, perhaps based on the ratio test. But what you really have to make sure is that your pivot element is positive. And if there's no positive pivot element, then the problem is undone. So after the pivot column is found, by choosing a negative entry in the Z row, usually the most negative, so it doesn't really matter. The negative entry in the Z row, there is no positive element in the rest of the column. Nothing that would be, there's nothing positive, you can't do the pivot, and you have to stop, and you stop and say the problem is undone. The only difference for a minimization problem, the only difference is that you're looking for something positive in the Z row. But then this positive remains the same. You always need your pivot element to be positive. Basic rule. If I see somebody pivoting on a negative element, which I will do, I'm absolutely sure, then I like 0 and 0 and come back. Okay. Any questions about this part? Part B is a formulation question. It wants you to start with a text like the one you can see here, and produce a linear programming formulation. And the linear programming formulation always has the three elements that I have already put captions for, which are decision variables, an objective, and a constraint. In this case, it's actually quite an easy problem. And the problem is that you have three different raw materials that you're using to produce some food for animals, oat, maize, and molasses. And you're only deciding how much of each of these three materials you want to use and mix them together and produce the food for your animals. This is a quite simple problem, and when you perhaps it takes some time to read through and think through before you come up with the right answer. My advantage is that I have the model solution from last year, so I know that you can you'll be fine with just 3 decision variables: the amount of oats, maize, and molasses to use. And that should be in tons per week. To get the objective, when you read it carefully, it's given at the end of the question, where it says that the cost of purchasing the materials should be minimized. So you want to minimize the cost of purchasing these materials, and the cost is given in the table for each of these. So if the cost per ton is 130 for oat, and you're buying X1 tons of oat, then this is 130 X1, and there's also 170 and there's 120 X3, and this is the cost. So that's quite simple. Now for the constraints, that's tedious. If we go backwards, the demand is 21 tons. That's a constraint which is saying that the total we want to produce is 21 tons per week. And because we're producing just by blending the 3 materials, nothing is lost and nothing is created in the process. That means that the total amount we need to buy is 21 tons. And the total amount we need to buy is X1 plus X2 plus X3. So that is supposed to be 21. All right? I don't know if it makes sense. It seems quite simple. If you have any questions, if something is not clear, start shouting. The next, keep going backwards in the text. You can do it. Up to down or down to up, doesn't really matter. Is that there is a certain limit on how much of the individual materials is available per week. So there is no more than 11.9 tons of oat and so on. 2 is less than or equal to 23.5, and X3 is less than or equal to, is it 0.75? And then the remaining constraints are about the content of protein and lipids and fiber in the final product. And this is, so these numbers in the table are the percentages. It means that 13.6% of oat is protein, etc. And you want the final product to have at least 9.5% of protein. Okay, that's the idea. This could possibly remind you of a problem that we did in the lectures, which was about producing some alloys, I think. So there was a required grade of content of copper and things like that, I think. Vaguely, I remember. So what you need to do here is that for the proteins, you want 13.6x1. That's the proteins you get from oat. That's 4.1 times x2, which is what you get from maize, and 5.3 should be greater than or equal to 9.5 times 21. The reason why 21 is clear to me, but isn't clear to everyone. Yes, that's correct. So this is the same 21 as here. The reason for this is, say, for example, if you only took oat for everything, so forget that there is a limit on how much oat you can take, but if you only took oat, 21 tons of it, then you would get not 21 times 13.6% of protein in your food, but only 13.6. So the content of protein really is this expression, this sum, divided by 21. So you want to put, well, either you can, or you can also write this divided by 21 is greater than or equal to 5, which is just as good. Yes?
They just scale.
Yes. Okay. So this is okay. So I'm answering your question now. Also, among other questions. So in fact, what you want, so if producing 21 tons altogether, and x1 tons of that is oat, then the relative content of oat in the mixture is x1 divided by 21. You agree? And if you take 10.5 tons of oat, then you'll get a half, and that will mean that among the 21 tons that you're producing, half of it is oat. Okay, for example. And this is the proportion in the final food, which is maize. And this is the proportion in the final food, which is molasses. So these are the proportions. Now, each of these gives you 13.6% of proteins or whatever it was. This gives you 4.1% of proteins, and this gives you 5% of protein. So you want this combined quantity to be 9.5. So these three constraints, as you can see, they're all the same. They're all equivalent. They all look similar. They all mean the same thing, and they're all correct. So either one of the three for the proteins will do. Is that fair enough? The constraint obviously is wrong if you don't put the 21 there, because then it's taking 2 tons of molasses would satisfy it, whereas obviously the final mixture would only have 5% of protein. So that wouldn't make sense. We do have to either divide the left-hand side by 21 or multiply the right-hand side by 21. And then there are the more constraints that are very similar. So for the lipids, you get 7.1 x1, 2.4 x2, 0.3 x3 should be greater than or equal to 2 times 21. And for fiber, seven x1 plus 3.7 x2 plus 25 x3 should not be more than 6 times 21. 1, I think. Any other constraints that are missing there? Yes? Wrong? Yes? He's wrong. You can say yours. Do you want to say non-zero? I thought you wanted to say non-negativity. Yeah. But they can actually be zero, but they can't be negative. And that is right. So x1 has to be non-negative, x2 has to be non-negative, and x3 has to be negative. And those are all the constraints that you need, and that finishes the question. Everybody happy? Let's move on to question 4. Let's quickly finish everything and then we can go. So again, I'll give you about 5 minutes to read the question, maybe 3, while I'm preparing an answer. Oh, this is a master.